Good afternoon, everybody. Last class, I think only one person attended, and so we just decided to say, let's go ahead with the class, irrespective of the number of persons attending. So today we'll be looking at review of data structures. We'll start with three data structure, though we've talked about linear data structure, array, linked list, and the stack and queue. So we'll talk about three data structure. A tree data structure is defined as a collection of objects or entities known as nodes, and these nodes are linked together to represent or simulate a form of hierarchy. The tree data structure is non-linear. When you say linear, it means they are straight. When you say non-linear, they are not straight because it does not store in a sequential order. And the tree data structure is a hierarchical structure. The elements in a tree are arranged in multiple levels. They are all arranged in multiple levels. In the tree data structure, the topmost node is known as a root node, and each of the nodes contains some data, and the data can be of any type. Each node contains some data and the link or reference of other nodes, which you can now also refer to as children. Let's look at the basic concepts of the tree. The tree here in our own data structure case is different from the normal tree you see in real life. So in the context of computer science, it consists of a finite order set of linked nodes, where each node has at most one parent node, zero or children node. So example, the tree we are looking at now, you have the nodes as A, B, C, D, E, F, G, H. A can be likened to as the parent. In this case, you can refer to it as the root. Unlike the normal tree you see outside, the roots are always at the bottom, but for computing trees, our roots are always at the top. So here you have A, B, C, D, E, F, G, H. And you have edges. Edges are the connection from one node to the other. You have A to B, you have A to E, B to F, B to H, B to G, E to C, and E to D. Properties of tree. Do they have properties? What we could use in identifying them? Yes. Every tree has one designated node, which we call the root, that has no parent. Every node except the root has exactly one parent. A node may have zero or more children. That is, you could have branches, which you call children, or you may not even have at all. There's a unique directed path from the root to each node. Tree terminologies, which we'll be looking at. We outline some tree terminologies in this particular class. Order tree, a tree in which the children of each node are linearly ordered, usually from left to right. Ancestor of a node, any node including the the V itself, that is the vertices itself, on the path from the root to the node. Proper ancestor of a node, V, any node excluding V on the path from the root to the node. Tree terminologies. Descendant of a node V, any node including V itself, that is the vertices itself, on any path from the node to a leaf node is in and a node with no children, you could refer to it as a descendant. Proper descendant of a node is any node excluding V on any path from the node to a leaf node. Subtree of a node, a tree rooted at a child of V. So these are some tree terminologies. You see it now, the proper ancestors of E, ancestors of G. Then you look at the tree on the right, proper ancestors of node H, proper descendants of node C, and then parent of node D on your left, child of node D, grandchild, grandfather of node ij, and grandchildren of node c. Then you see the right subtrees of node a. They are all labeled. Continue with the terminologies. We have the degree. The degree of a tree is the number of subtrees of that particular node. When you say subtree, that is other smaller branches you can link to that particular node. So the number of those branches is what you could call the degree of the node. A leaf node is a node with degree 0. That means it doesn't have any children. It terminates there. Internal or interior node is a node with degree greater than 0 and is called an internal or interior node. Siblings. Siblings are nodes that have the same parents. And so nodes that have the same parents, they are all called siblings. Size. The size of node in a tree. The number of nodes in a tree depicts the size, refers to the size of that particular tree. So you look at the siblings of A related to A, siblings of E, they descended from A, so they are all related to E. Level or depth of a node. The level of a node is the length of the path from the root to the vertex. Height of a node, V. V here refers to the vertex, that is the node we are talking about. The height of a node is the length of the longest path from V to a leaf node. The height of a tree is the height of its root node. So by definition, the height of an empty tree is -1. So the height of the tree above is 4. Look at it, level 0, that is the root, level 1, 2, 3, 4. While the height of node C here is 3, height of node G here is 2, height of node J is 1, and then the height of node K is 0, as the case will be. Importance of trees. Trees are fundamental data structures in computing. They are suitable for one, hierarchical structure representation, like file directory you have inside your computer, where you could have drive C and all other sub-drives that are linked to drive C. Organizational structure of an institution, where you could have a vice chancellor, the deans, the HODs, the lecturers, then the students. Class inheritance tree. Then problem representation, you can also use trees to represent problem like expression tree and decision tree, which you use for computation. Then 3, efficient algorithmic solutions. For example, search trees are used to design algorithms you can use in implementing searching. Efficient priority queues through heaps. Then let's look at a kind of tree called binary tree. A binary tree is a tree for which each node has at most 2 children. At most means the maximum number of children that particular node should be having is 2. So a binary tree is either an empty tree or a tree consisting of a root node and at most 2 non-empty binary trees. A full binary tree is either an empty binary tree or a binary tree in which level k greater than 0 has 2k nodes. That is, it is either empty or when it is full, it has the root node. Every other node has 2 children like that. That means it is full. A complete binary tree is either an empty binary tree or a binary tree in which each level of k greater than 0, that is the level now, the height, other than the last level contains the maximum number of nodes for that level, which is 2k. The last level may or may not contain the maximum number of nodes. So if a slot with a missing node is encountered when scanning the last level in a left to right direction, then all the remaining slots in the level must be empty. So every full binary tree is a complete binary tree, but the opposite is not true. Every complete binary tree may not be a full binary tree. Where do we apply binary tree? Binary trees have many important uses, and 2 of the examples we are going to cite are: 1, binary decision trees. They are used in internal nodes and maybe their conditions. The leaf nodes denote decisions. For representing arithmetic expression, then we have the BST, binary search tree, which is a binary tree that is empty or that satisfies the BST ordering property. The key of each node is greater than each key in the left subtree, if any, of the node. And the key of each node is less than each key in the right subtree, if any, of the node. So each key in a binary search tree is unique. This is an example of a binary search tree. Importance of binary search trees. Binary search trees they provide excellent logarithmic time performance in the best and average cases. Table 1 shows the average case complexity of using linear data structures compared to binary search trees. Average case complexity of using linear data structure compared to binary search tree. These are a data structure. In terms of retrieval, binary search tree is very fast, insertion fast, deletion fast. For sorted array, in terms of retrieval, it is fast. For insertion, it is low, and then for deletion, it's low. For sorted linked list, in terms of retrieval, it is low. In terms of insertion, it is low, and in terms of deletion, it is low. So the binary search tree performs better than each of these data structures. Tree traversal. Tree traversal is the same thing as movement within the tree, moving from one node to the other. So tree traversal is the process of systematically visiting all the nodes in a tree and performing certain computation at each node in the tree. And we have two types of traversal method: breadth first search and depth first search. Breadth first search. Breadth first search traversal proceeds as follows. You visit first all the vertices that are adjacent to a starting vertex, then all unvisited vertices 2 edges apart from it, and so on, until all the vertices in the same connected component as the starting vertex are visited. Figure 1 will give us an example of breadth first traversal. Breadth first search traversal. This is H. From H, you come to D. From D, you go to L. From L, you go to B. From B, you go to F. From F, you go to J. From J, you go to N. From N, you go to A. A, you go to C. C, you go to E. Then you go to G. You go to I. You go to K, M, and O. Breadth first search. Depth first search traversal is further classified into three types, which you may have been used to: pre-order, in-order, and post-order traversal. The types are summarized in Table 1. An example of the type are given in Figure 2A, 2B, and 2C, respectively. So this is pre-order: node, left, right; in order: left, node, right; post order: left, right, node. What it means by pre-order is you visit the node first, you are pointing out, then you visit the left node and the right node. Then for in order, you visit the left node, you now visit the node and right. Post order, you visit the left node, the right node, then the node. So here you visit the node, visit the left subtree if any, visit the right subtree if any. Depth first search, NL arrow. NL arrow is the pre-order. So you come here, you visit the node, you go to left, you go to right. So you come to the node, then you now go to the left. After visiting the node, you are now in D. You are now in this particular node. You go to the left again. You are in this node, you go to the left. Yes, when you now go to the left, you now go to the right. You are through with this. Then you now come here. F. You visit this particular node. You go to the left, and then you now come to the right. After that, you come to L. You go to the left. Then you go to the left again. you now come to the, no, you go to the left, you go to the left again, you now come to the right. Then here, N, you go to the left, you come to the node, you go to the right. Here, you come here again, you go to the left, you come to the node, you go to the right. Okay, that is correct. Depth first post order traversal, left, right node. You come here, you go left, 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 left. You are here now. Then from left, you go to right. You now visit the node. Then you come here again, where you have your D. You are not going to left. Then you now go to right. You go to left. When you go to left, from left, you go to the, come back to the, what do they call it? Go to the right and then visit the node. You are done with it. You come to where you have H. You have gone to the left. You now come to the right of H, and that is where you have L. When you have L, you go to the left, you go to the left, which is I, you come to the right K, you visit the node. You come here again, you are not having any left again, you go to the right. When you have the right here, you go to the left M, you go to the right, you visit the node. Then you come back, you visit L, you come back, you visit H. That is for